Hi, I Aziz welcome you to CoedMaster, and in this video I am going to talk about bitwise operators. So let's get started. In previous video we talked about bitwise operator and we saw that bitwise operators are faster than other operators. The reason is super simple. The bitwise operator works on the binary representation of a number. So I would say that it's kind of a low-level instruction. And whenever we run a low-level instruction, it's generally faster than high-level instruction. That's why bitwise operators are faster than normal operators. If I talk about Java, there are 7 bitwise operators in Java. Number 1 is bitwise AND, bitwise inclusive OR, bitwise exclusive OR, bitwise complement, bitwise left shift, bitwise right shift, and bitwise unsigned right shift. And in this video, we are going to learn all of these 4 bitwise operators, right? Okay, moving on. So before we understand how bitwise operator works, let's understand how integer works. In Java, 32 bits are used to store and represent integers, right? But just for the sake of the example or just for our understanding, in this video we are only going to use 8 bits to represent any number, right? So if I ask you how many numbers are possible if we have 8 bits, it means if I set all the bits to 0 till all the bits becomes 1, how many numbers are possible? So it's simple. 2 to the power 8, that is equal to 256. It means there are 256 numbers are possible if we have 8 bits. Okay. And if I ask you what will be the range of the numbers, then in case of integers, as integers also has negative numbers, the range comes out to be minus 2 to the power 7 to minus 2 to the power 7 minus 1. It means minus 128 to 127. And how many numbers are there between minus 128 to 127? So there are 128 negative numbers and one is 0. It means all the bits are set to 0. It gives 0. And 127 are positive numbers. So if we total all the numbers, we get 256 numbers, right? Okay. So this is all about how Java uses 32 bits to store and represent integers. So let's move on to our first bitwise operator, and that is AND operator. You might have studied AND gate in digital electronics. So that AND gate is used behind the scene to perform AND operations in Java, right? And so the symbol used to represent AND operator is ampersand. Now let's quickly see the truth table of AND operator. So what is truth table? Truth table basically tells at which condition your output becomes true. As this is a binary operator, it means we need 2 operators to perform this operation. So let's say if 2 operands are 1 and 1, then it gives 1. If 2 operands are 1 and 0, it gives 0. If 2 operands are 0 and 1, it gives 0. And if both are 0, it gives 0. So you can clearly see here that if both the operands are 1, then only AND gives result as 1. Otherwise it gives 0 in all the cases. So let's understand this with an example. So let's say I want to AND 9 and 8. So the binary representation of 9 is 0 0 0 0 1 0 0 1. And as I said that we are using 8 bit here to represent any number. So these are 8 bits. The first bit represent 2 to the power 0 and this bit represent 2 to the power 3. 2 to the power 3 is 8 plus 2 to the power 0 is 1. So 8 plus 1 is equal to 9. Okay, so this is the binary representation of number 9. And here the binary representation of number 8 is this. Only 2 to the power 3 bit is set, else other bits are set as 0. Now if we do AND of both the numbers, then we get 0 0 0 0 1 0 0 0. Why? Because we get 1 only if 2 operands are 1, right? So here 2 operands are 1 on 4th position. So that's why we are getting 1 on 4th position, else all the bits we are getting as 0. Because 1 and 0 is 0, 0 and 0 and is 0, 0 and 0 and is 0, and 1 and 1 and is 0. And remaining zeros are already 0. So we get output as 8. So this is how AND operator, bitwise AND operator works. Clear? Okay, moving on. So the next bitwise operator we are going to study is inclusive OR operator, right? And the symbol used to represent bitwise inclusive OR operator is this and we call it pipe symbol, right? And this symbol is used to represent bitwise OR. So let's quickly see the truth table of bitwise OR. So if two operands are 1 and 1, we get 1. If two operands are 1 or 0, it means 1. If two operands are 0 and 1, we get 1. And if two operands are 0 and 0, we get 0. So here if you observe closely, you can see that if any of the operand is 1, then we get 1. Okay, so the condition becomes if any of the operand is 1, then we get 1. If both are 0, we get 0 simply. So let's understand this with an example. So let's say if you want to OR 9 or 8. So the binary representation of 9 is 0 0 0 0 1 0 0 1. And similarly the binary representation of 8 is 0 0 0 0 1 0 0 0. And we simply want to OR 8 and 9. So in case of OR, what happens? So any one operand is 1, then we get 1. So in case of 1 and 0, we get 1. In case of 0 0, we get 0. In case of 0 0, we get 0. And in case of 1 and 1, we get 1. Why? Because in both the cases, one operand is 1. That's why we get 1. So the output of a 9 or 8 comes out to be 9. And this is the binary representation of 9. Clear? Okay. Moving on to next bitwise operator. So the next bitwise operator we are going to study is bitwise exclusive OR operator. And the symbol used to represent bitwise exclusive OR is a caret symbol, right? And we also call it XOR operator. Now let's quickly see the truth table of this operator. So in this, when two operands are 1 and 1, we get 0. If any of the operand is 1, then we get 1. Here also same. And if both the operand are 0, we get 0. So we can say that the exclusive OR is little bit strict than OR operator. Why? Because in OR operator, we are getting 1 if any of the operand is 1. But in case of XOR, we only get 1 if either of the operand is 1 and the other operand should be always 0. It means if this operand is 1, then it must be required that the second operand is 0. And if the first operand is 0, then it is required that the second operand is going to be 1 only. Then only it gives 1 as a output. So let's understand with example. Let's say I want to XOR 9 with 8. So the binary representation of 9 is this and the binary representation of 8 is this. And if we take XOR of this, we get 0 0 0 0 0 0 0 1. And the decimal representation of this binary representation is 1. Why? Because in only this case we are getting 1 here. In all other cases we are getting 0. So this is all about XOR operator. Now let's move on to next operator, that is bitwise complement operator. And the symbol used to represent bitwise complement operator is tilde. Okay, and this is a unary operator. So it means we only required one operand to perform complement operation. Okay, so the truth table of bitwise complement operators is if the bit is 1, then it converts that bit to 0. If bit is 0, then it converts that bit to 1. Let's see with an example. Let's say I want to complement 2. So the binary representation of 2 is 0 0 0 0 0 0 1 0, right? And if you want to complement this, then what it does, it simply inverts all the bit. It means 0 becomes 1, 1 becomes 0, 0 becomes 1, 0 becomes 1, and so on and so forth. And the value of this comes out to be -3. Why -3? I will explain you in a bit. Okay, now let's see the another example. Let's say I want to complement -2. As we can see that the binary representation of -2 is this. So let's write this as it is and do complement of it. So what this operator does, it simply invert all the bits. So it inverts 1 to 0, 0 to 1, 1 to 0, 1 to 0, 1 to 0, and we get our answer as 2. So if we are passing positive 2, it's converted to negative, and if we are passing negative, we are getting positive. I will explain you in a bit. So let's first understand how we represent negative numbers in integers. So in integers, the MSB bit is used to represent the negative numbers, right? So it means, let's say we have a number, and we have represented this number in 8 bits. So if the last bit, and that is the most significant bit, is set to 1, it means this is a negative number, right? And if the last most significant bit is 0, it means it is a positive number. So the last bit is used to set the type of the integer. If it is 1, it means it is negative. If it is 0, it means it is positive. Okay, so far so clear. Now there are few things you should remember, and that is how positive numbers are stored in memory. So it is simple, we just convert the decimal number to binary number and we store as it is. This is the simple story. So in case of 2, we simply convert this 2 to binary, and the binary representation of 2 is 0, 0, 0, 0 and 0, 0, 1, 0. So this binary representation gets stored in the memory. Okay, clear. So this is all about positive numbers. But there is a twist in negative numbers. So how negative numbers are stored in memory? So basically the negative numbers are stored in memory in 2's complement form. How? So let's say I want to store -1 in memory. So how it is going to store? It first calculates the 2's complement of 1. So and how to calculate 2's complement of 1? We simply write the binary representation number. We simply write the binary representation of a number, and this is the representation of 1. We invert all the bits from 0 to 1 and 1 to 0, and we add 1 to it. So this way we get the 2's complement of -1, right? So in place of -1, this binary representation gets stored in the memory. Okay, so far so clear. It means if you have positive number, then it simply converts decimal to binary and stored in the memory. But if you have negative numbers, then it is stored as a 2's complement form. So far so clear. Now let's understand the formula for 2's complement. So after doing all the process, the formula comes out to be 2n minus x. It means any number that is stored in 2's complement can be represented using this formula. And what is n here? N is equal to number of bits and x here is 1. So it means to represent 1 in negative form, we can write 2 to the power 8 minus 1. It means when all the bits are set, see the most significant bit is also set to 1 and all other bits are also set to 1. It means it is represented as -1. Okay, now let's say I want to represent -2. How it works? Binary representation of -1 is this, right? And now I want to store 2. So what I do, I basically unset the second bit because second bit is corresponds to 2. So this way this binary representation represents -2. And how it is possible? Because we say that if all the bits are 1, it is represented as a 2 to the power 8 minus 1, right? And let's say if we want to represent -2, so we simply unset the bit of 2. So it becomes -1 -2. So that's why we get our output as -3, correct? Let me show you once again. What we did in a previous example, we simply going to store 2 and we are performing tilde operation on it. It means complement operation, and we are getting -3, right? Because -2 are stored in a 2's complement form, and the 2's complement form and the value of 2's complement form is -3, correct? And how it is working? Because if all the bits are 1, then it is represented as 2 to the power 8 minus 1 in negative numbers. And if you want to represent 2, then we simply unset the bit of 2, right? And we subtract from it. So we get 2 to the power 8 minus 3. It means our -2 is represented in 2's complement in the form of -3. I hope you got it. So basically what it does, whenever we pass negative numbers, it converts it to positive number. And whenever we pass positive numbers, it gets converted to negative numbers. So this is the basic role of complement operator. So in this video, we have discussed 4 operators. Number 1 is the AND operator. Second one is inclusive OR operator. Third one is exclusive OR operator, and the fourth one is NOT operator. So I hope now you have good understanding about all the operators and how it works. In next video, we are going to discuss about left shift operator, right shift operator, and unsigned right shift operators. So this is it for this video. Thanks for watching. See you in the next video.